Objective, so we want by the end of this for you to be able to understand the basics of the chill beam. If we don't, I have failed, and I'm sorry, but let's hope that's not the case. The other part would be understanding the general benefits of decoupled cooling systems, specifically the chill beam type of system. Understand the unique challenges, or sorry, design aspects of a chill beam system and how to implement good practice principles for new or retrofit projects. Identify appropriate applications for chilled beam products, and then select the proper types of chilled beams based on um, specific project requirements. So we want to first start off with the basics, and Matt had kind of talked about, generally, what are we talking about with decoupled cooling systems? What does that mean? Breaking out the sensible versus latent load, and then how a chilled beam works. And we'll dig into some of the more different types of products that we have out there in the industry that you can select from. And then common applications. So this is where we'll go through those case studies, whether it's commercial office spaces or laboratories, which I know you see a lot of in this market particularly, and then design considerations. So that'll be kind of the meat of the conversation where we get a little more technical. And definitely, if you've got any questions, feel free to interrupt. If I say anything outlandish, definitely don't throw anything at me, but maybe raise your hand, and we'll try and address it during the discussion. So has anybody, don't count Matt's session earlier, because that's cheating, but before this, have you ever heard of a chilled beam? Do you know what a chilled beam is? Yeah, good. Okay. So lots of familiarity with it. Well, in case you haven't, it is essentially defined as a sensible only cooling device, which means that a lot of the products, they have horizontal coils within the units. They're meant to be dry coils and operated the chilled water above the dew point in the space a couple degrees. And so those stay dry, but it's handling just your sensible load in the space. So that's the usual intent when we talk about chilled beams. The primary air is used to treat the latent loads in the space itself. So when we talk about, again, dry coil applications, there's different types of units kind of across all different manufacturers. The ACBL linear, this is probably the most common. If you've dealt with chilled beams before, it's probably the one you've seen. That can come in a 1 inch, sorry, not a 1 inch, that'd be incredible. A 1 foot wide unit or a 2 foot wide unit. And they basically run 1 foot increment lengths up to from 2 feet up to 10 feet. And so you can run those continuously or have them discrete throughout the space. There's also the active chilled beam cabinet unit. So these are typically in teaching lab spaces or classrooms where you put them underneath the window areas and provide cooling and heating and deliver the air actually in a displacement ventilation pattern. Have you heard of displacement ventilation before? You use that. So the intent with that is to actually stratify the air, not de-stratify, and allow the heat loads to pull the air throughout the space instead of being pushed and churned uniformly throughout. So that's kind of unique and neat because you get the benefits of the decoupled chill beam system, but also that displacement airflow pattern. So that's commonly used in classroom applications. The passive beam, which this is kind of reversed because you always think of starting with this type of concept. The passive beam is kind of the earlier invention, or the one that came first, where you've got just buoyancy driven airflow. So passive being that you don't have a primary airflow connection to it. So it's just using natural buoyancy and that warm air getting up behind that coil and cooling off and falling down into the space. So it's supplemental or an auxiliary cooling component to the system. And then the modular style 2-way, 3-way, 4-way unit, where if you have like a small office space, maybe it's on a dual wall, two walls that are perimeter, glazing, you can have the 4-way discharge to kind of keep the discharge throw down and maintain proper comfort. So that's a good one to consider. And then the recessed unit, which Matt had shown earlier, where it was installed up behind the dual slot diffuser. So lots of options. And then I know this is going kind of back on what I was just saying about sensible only, but there's also, in the industry, induction units, but kind of updated to have the chill beam type of technology, the new nozzles and design that exist with the chill beams. So you can actually design some of these to have drain pans within them. And I'll show you a video in a little bit later in the presentation showing kind of the operation of, when those start to condense, how does the water fall down into that drain pan? So you can kind of see how that operates. The LIU is essentially that 24-inch wide unit, but it's a little taller because it has an A-frame coil inside of it. So it allows us to capture that condensation. And then you can put drain pans throughout some of these other units as well. All right, so Matt talked about this earlier. Essentially, we're only running, a fourth to a sixth parts of primary air to the chill beam. And again, you're usually mixing and moving a lot more air changes than a traditional system, just by the nature of that induction process. So when you dig into the parts of the cross section of that cabinet unit, you have a lot of those same internal components. You've got a primary air inlet usually on the side of the unit, and it could be either side, where you're pressurizing that plenum. So you're doing kind of the same individual internal components as the 24-inch wide linear, and then you're inducing air horizontally through that water coil, and then it's mixing with that primary air and discharging at low velocity and low level into the space, creating that displacement pattern. So again, that's got a bank of nozzles as well. It can come with, four pipe heating cooling, but also a fin tube option. So if you kind of decoupled or separated the hot water line to running a fin tube underneath the windows, that's an option as well. And then again, the passive beam. So this usually needs some amount of free area on either side of the passive beam footprint as well to allow for that warm air to get up into the ceiling void, or if it's exposed, just up around that passive beam to cool off. So you might put these above, high heat equipment, or in walkways or near the perimeter where you need additional boost of cooling. And we've seen these implemented with all air mixing systems or underfloor displacement style air distribution systems, so they can kind of be mix and matched as well. So in general, you're going to see benefits of comfort, and that relates to what Matt was talking about, where the discharge air temperature, because you're bringing in 55 degrees on the primary air, but 4 to 6 parts of the discharge air is from the room side going through that 58-degree chilled water to 60-degree chilled water. So the mixed air and the discharge air temperature is actually warmer than your typical overhead all air system. We get energy savings from less horsepower on the fans because we're reducing the ductwork size and the amount of air that we're moving throughout the building quite substantially in a number of cases, and that can reduce the amount of fan horsepower that we need for the building. There's also opportunity to eliminate terminal reheat. So because we're modulating that water valve within the local space itself, you can control the sensible cooling or heating there locally in the space. So you're not doing large reheat, and that really comes into play with hospitals or lab applications as well, which we'll talk about in detail. And just to reiterate, so we're talking about a number of decoupled systems today. You've got the fan-powered DOAS product option, but the chill beam products do not have filters in them or fans. So it's really just operating off that pressurized plenum and using that nozzles to induce the room air. There's not fans locally either within the unit. You might have a VAV box upstream of the chill beam to modulate the airflow, but other than that, not many moving parts. And again, reduced ductwork, we talk about that, and mechanical equipment size. So here's an example of the Oracle building in Texas. You could see the continuous style 24-inch wide linear units. And then let's see, I think this particular project actually added white noise to the building because the chill beam systems were very quiet. Really, if you start to get into the 0.8 inches of water column of static pressure or higher, that's when you start to typically register, a higher NC level, but otherwise in the usual range for chilled beams, they're very quiet, quiet systems. Okay, won't spend much time on this because Matt had mentioned it in the earlier session, but essentially the core benefit in concept with the beam is that we're shifting all that energy transport over to the water side and not using large air duct shafts to move all the energy throughout the building. So it's more effective in that sense. Moving on to how that relates to savings. Can anyone mention or maybe throw out why you see different energy savings, based on what we've kind of talked about in the morning session here? Why are we seeing different potential energy savings throughout these different applications? Humidity? Okay. Yeah, a lot more air for labs. Yeah. Yeah. Hours of operations. Yeah, that's a good one. Yeah. Yep. Yep. Makeup air. Yep. That's a good one. So you could see that anything else before I go on? Those are all really good answers. And a lot of that comes into play really with, if you think about offices and healthcare, you're seeing a similar energy savings potential. A little bit more with healthcare because again, the outside air change rates, the minimum that's required for these spaces are really dictating how much we can reduce it with the chilled beam system. When you think of labs, they have such a higher heat load. Most cases you've got high load driven labs, but you still have that 2 to 6 air change per hour requirement. But a lot of the additional air changes in a lab, are typically, sensible heating and cooling, sensible cooling. So that's kind of where chilled beams really shine. So allowing us to shift really as much of that sensible load over to the water side. So when we talk about laboratories, there's and this is actually an older ASHRAE article. Chilled beams, like I said, has been in the industry for over 2 decades now. Just in North America, it's over in Europe, it's been utilized for a lot longer. But this was a study published in ASHRAE, a journal article, and key takeaways: essentially eliminating that reheat was really big for them, and also reducing the outside air handler and ductwork size contributed to a number of these savings. So this was taken from that Tahoe Center, which was the highlight project in that ASHRAE journal article. So you can kind of see and we summarize on the left side there that we were able to reduce the CFM for the project quite significantly. The tonnage down to 20 tons as opposed to 35 tons for the all air system. And then mechanical cost even ended up being fairly neutral to slight savings. So, you know, um, that added with operational cost reductions for each year. Yeah, right. Yeah, so glad you asked. There's a snippet showing the differences between the active chilled beam system, which is on the left, and the all air system. So the standard VAV reheat system, showing a couple things, basically all throughout the year, even if it's 20 degrees outside or 90 degrees outside, you've got 55-degree air that's being driven throughout the spaces, really, because you've got different load profiles within the labs. So you've got the high load lab that's driving, supplying 55 degrees into that space, and reheat coils that are engaged, I guess, on these top two delivery points. So that's discharging 65 to 68 degrees because, again, that minimum air change requirement is driving a high amount of air volume into the space. So you're balancing that load. With the chill beam system, you can basically cool on the local requirements within the lab space. And they can all be different lab heat load requirements, but you can modulate those water valves based on that local load. And there's a number of things that could also come into play with like hood diversity, right? Where you're not designing for every fume hood to be wide open. You might have some diversity there where you're designing for you know, a certain percentage of those fume hoods to be fully open. And the ventilation air can swing. So they're showing, whether it's a cold to hot day or even moderate day, that you can adjust that outside air, ventilation air temperature, go into those chilled beams, and then you're just, providing the heating or cooling locally at the chilled beam. Yeah, so you're still going to have your fume hood exhaust. So chilled beams are good for high load, like load driven labs. Exhaust driven labs, you're going to have other makeup air diffusers, something to supplement the chilled beams or a different approach altogether because it's such a high exhaust rate. With the chilled beam designs, typically you'll have still the fume hood exhaust and general exhaust, and you balance the supply air to the chilled beams based on the total exhaust for the room between fume hood and general. So you have that negative pressure design still. Right.
So chill beams just solution situation.
Well, the
More constant volume type of lab rather than exhaust change constantly.
so you could put a Venturi valve on the upstream of the chilled beam as well. So it's fast acting and it kind of operates with that that sash velocity. Right. Yeah, so you would design it for kind of your min and max condition and just making sure that it stays within really the plenum pressure within the chilled beam is critical for us. So operating between 0.2 inches to 0.8 inches of water column and just making sure that those conditions that you're mentioning are within that range. And you won't lose induction rate, you won't lose detachment or Coanda effect, and things like that. Yeah, very good question. So in terms of having separated exhaust, is that what you're talking? Yeah. So yeah, so some of the ones we've seen more recently, like there's a jumping a little bit ahead, but a University of Maryland project that was a project highlight in ASHRAE. They had a manifold exhaust system, which I think I'm seeing some head nods. That's becoming a common approach where you manifold and combine those together and you essentially just make sure that it's diluted enough. I know it comes down basically to the client requirements for contaminant concentrations or the dilution in the exhaust, but we've seen it to where you're combining the general exhaust with the fume hood exhaust and doing research to make sure it's diluted enough with that approach based on the types of you know specimens or items that they're researching. Yeah, really all the chill beam needs is the water valve adjustment and then the VAV to your point. So yeah, the control modules themselves would either be the smart thermostat or the controller on the VAV box, and outputs would run to the water valves for the beams. Yeah. Yes, very sorry about that. So that probably didn't make too much sense on there. Okay, so getting into the different types of applications. So you saw this or part of this project earlier with the guy playing putt putt, and I don't know who has time for that. But LEED Gold, so Oracle was able to attain LEED Gold, and that 30% energy savings over the ASHRAE baseline, 23% of that 30%, or sorry, the 23% was fan energy, so the majority of that 30% energy savings was from fan energy. So reducing that horsepower. So that's kind of lining up with what we were talking about earlier on the benefits. Office space design, usually latent is driving your primary air for those cases. So you're really not down to your ventilation airflow rate. And we'll go into this detail in the software section in the afternoon. But you'll kind of see where your minimum ventilation might be 0.2 or less CFM per square foot, but you're actually up to 0.3 or 0.4 CFM per square foot just to drive the, take care of the latent conditions in the space. And then this is the other example. So Matt had kind of talked about the slot diffuser design with the recessed chilled beam at the perimeter. On the interior space, you typically run a two-pipe cooling only throughout the interior, and at the perimeter, you would have some sort of either a switchover valve or a four-pipe system, which this had here is a four-pipe heating and cooling pipes ran to the recessed unit there. So fairly simple system from a piping arrangement. Was that meant for me up there or no? Okay. So kind of peeking back behind what's going on behind that slot. This is in our tech center. This was not an actual project. I know we've got exposed, wood, combustible, right? But this is just for display purposes only. But you could see that really you've got that recessed unit coupled very closely to that slot diffuser. So architecturally, you could really align that to any sort of linear type slot diffuser and match the aesthetics requirements in the space, but still get that chill beam to be installed. So drain pan wise, if you were to design a wet coil design, the vertical unit is the only one that you could put a drain pan on. There's horizontal recess units, but that coil is horizontal as well, right? So that you can't really put a drain pan in front of because it'll block all the induced air. So just something to keep in mind if you're looking at that. Consider ceiling space for the vertical design, which is what's shown here. There are particular types or models that can come with a drain pan, but most, if not all of these cases we're reviewing today are dry coil applications. So 58-degree or warmer chilled water supply. We've done a number of installations at the U of Arizona, University of Arizona, and this particular project, it's probably a little hard to see, but over on the right side near the perimeter area, we have the exposed open ceiling 24-inch wide linears, but there's a wing on the side of it as well, and I'll talk a little bit about that. If you have an open ceiling, there's options across manufacturers to have wing extensions to maintain that coanda effect. So even an open ceiling without that, ceiling grid, ceiling tile next to it, we can still maintain proper air distribution. Does everybody see where the other units are as well? Take a guess. In the soffit, yep. So the perforated soffit here, and so that's a horizontal unit because you can see the wider face with access fasteners on that side. So you don't really need to maintain much, but every once in a while, if you have like hospital rooms, lint or fabric that's getting up there, you could just vacuum that off, clean that off pretty easily because it's not a wet coil again. So here's the install of Winchester High School, and these are all not active cabinet units. So you might have 2 4 or 6 foot long units per classroom or teaching room, but there's inactive blank sections that kind of allow it to be a continuous look. So you can utilize it also you can make bookshelves in there, there's all sorts of options and accessories to make it actually functional. And then you've also got the drywall chases on either side of the classroom that's hiding the ductwork. So the ductwork comes down and connects to either side of the cabinet unit. And then here's open ceiling space installations. So here you could see on the bottom right and the left photo that it's got a, yep. So cooling will be winter cooling or?
Yeah.
Yeah, so you've got the water coil inside of the unit that the room air is inducing into, so you could run chilled water to the water coil inside of the unit.
Is that what they?
Yeah, I mean, I don't know. Yeah, I'm getting head shakes from the dean in the back. So the question was, I'm sorry, I'm really bad at this. I'll repeat the question, but just the question here for those online was, how are they doing cooling in the winter? So when all the students come in, it's midday, and there's a cooling requirement even in the winter. Yeah, so they'll modulate the cooling coil. The primary air temperature might reset based on the requirements of the project. Yeah, so the question was in regards to four pipe requirements, how do you sort of handle some classrooms being cooling and some classrooms being in, you could have a four pipe system where you've got, water valves for each, or you could do a six-way changeover system if you wanted the two pipe approach in there as well. So you could do four pipes throughout the building, but two pipe at the chill beams, and you switch that over with the six-way valve. Anything else? Everyone online's good? Gonna force their, nobody's sleeping over there. But yeah, no, enter questions online if you got any questions as we're going along. So open office, basic point here is, just ensure that you're selecting Coanda wings. If you've got a really tall space, like, 12, 14 feet or higher, maybe you actually don't use the Coanda wings, and that's going to have a sort of a 45-degree discharge down into the space. That's been something described below. So this is from our tech center in Swanee. You can kind of see the fan column over there blocking some of the smoke on the left. So this is an open ceiling, obviously, installation. And you can notice that without the Coanda wings, that's throwing nearly downwards to 45 degrees into the space. And then when it switches over on the right side, you can kind of see those Coanda wings maintaining that horizontal discharge a lot better than if you didn't have those. So, and those can be for, discrete units or continuous application like what's shown here. All right, so this was a load-driven lab. You can see a lot of the equipment throughout the space, no fume hoods in view. This, there's some modularity or flexibility in terms of where you can place the chill beams, but most critically, obviously you don't want any collisions of the airstreams to have discomfort, but also the fume hood velocities. So just making sure that if you have fume hoods, that the discharge pattern is not going across that fume hood, because that's critical. So this being load-driven lab, no fume hoods. We've got continuous linear beams up in the ceiling. They're located above the aisles, and 2-foot grid, about 8 feet across. So just a lot of the software tools, including the price software tool, allows you to look at throws and collisions based on the distance you're placing them throughout. So if you haven't seen that before, we'll try and walk through that in the afternoon. There's also pattern controllers as well that can orient the airflow to be shorter or the standard throw distance. This was a project here locally we did several years ago. These particular units are the 12-inch wide linear unit, and it's actually right next to the luminaire, the lighting system within that 2-foot grid. If only there was a chilled beam with lights integrated into it. Stay tuned. There is. But you can see that these are actually located above the fume hoods. So we have fume hoods in this case, but just making sure that, again, if they are above the fume hoods, that there's absolutely no collisions, or opportunities to move airflow across those sashes. All right, so there's a case study that I referred to a little bit earlier from the earlier questions. So this was a University of Maryland ILSB building. They achieved LEED Gold, and you can kind of see the specifications there. 44% energy savings over the baseline, and their payback was really quick. So not quite the same first cost as we saw from the Tahoe Center earlier, which was rather cost neutral. This one had about 3/4 million first cost premium, but they were able to recoup that pretty quickly because of the energy savings. Do I need to repeat that? Okay. So Jason online asked if placing the chilled beams directly above the fume hood is a common approach. And I would say in most of the cases we've seen, they're located in the aisles or above the equipment or workstations, not above the fume hoods. But if you were to do that, again, just make sure that it's, you don't have any collisions, or those beams were spaced quite far apart. So just ensure that, yeah, you're not having any collisions or high velocity down near the fume hoods. Okay, so I know there's a lot going on this slide. We won't go through all of it, or maybe it will. But the air handling unit style was a dual wheel enthalpy and sensible energy recovery. Now, with labs, a lot of times, if not nearly all the times, the air change requirements are driven by the owner or client themselves. And they did research with this dual enthalpy wheel design where they measured the contaminant that was showing up in the manifold exhaust system. So we kind of talked about this a little earlier, where you're bringing the fume hood exhaust and the general exhaust grill and mixing that and bringing that back to the wheel. So obviously you've got the wheels that are exchanging the energy into the supply air, but you also don't want to bring contaminants into that supply air. So they did studies to ensure that the contaminant concentration, and this is all described in the ASHRAE article, to make sure that was below the threshold required by the owner. So kind of a unique approach, but what it allowed them to do is provide neutral air delivery to the chill beams. So they've got 68 degrees Fahrenheit running to the active chill beams for that primary air, or that minimum air change requirement, to match the general exhaust and fume hood exhaust. And they were able to reduce the airflow by half, which is quite substantial. Here's another view of it. So what the active beams essentially allowed the project team to unlock is less noise generated. So it allowed them to keep a fairly sufficiently low NC level in the space, and space cooling and heating and cooling reductions of 55 to 67% respectively. So that kind of lines up with those earlier pie charts I was describing earlier. And then ease of maintenance as well. Next up is healthcare. Is anybody working on healthcare projects at this point? Okay. So chilled beams with healthcare, there are some allowable spaces that it's actually a more recent ASHRAE 170 publication that allowed in the addendum the recirculation component of the chilled beam. It's been in the addendum a while, or a part of the standards, but now it's been moved into the main body of the ASHRAE 170 for recirculation units in the space, and whether you need filters in the chilled beams or not. So that's a really critical item to look at. But first, before getting to ASHRAE requirements, you can see that you've got different orientations of the chilled beam within the patient bed. There is a preference to having the chilled beam on the right side, where you're discharging away from the headboard and kind of covering the window glass area on the right side. So that's a really sort of, I'd say, optimized location. You can see though that there's lights directly above the patient bed, which are required, so it's offset the chill beam location. This one on the right, you can see the perf is a little bit different than the one on the left. Why do we think that is? to get a little bit more tighter hole pattern. So the one on the right is a sort of a mental health ward on the right side. So they've got anti-ligature requirements for those spaces. I can't ask about the perf and the discharge, but there is. You can't quite see it. Those online might be able to see it, but inside of that perf, inside of that discharge, there's actually perf as well. So nobody can, put anything up in there and per those anti-ligature requirements. And then there's also tamper-proof fasteners on the face as well, so you can properly clean the coils. Next up here, again, you can see that the orientation is parallel to the patient bed and right next to that light above the patient. So again, really good distribution through that orientation and configuration. So this is what I was alluding to earlier. So in the healthcare 170 standard, there's a number of spaces, and the table was recreated, pulling from the ASHRAE tables. This isn't directly from ASHRAE. But just kind of highlighting the categories and the room spaces that you can put recirculation room units in there. So what ASHRAE 170 allows you to do is, you still have to have your minimum outside air change requirement, which would be the primary air component running to the chilled beam. But any difference from your total air changes can be utilized through the recirculation amount of air through from the room side through that water coil. The important thing is just to make sure that, if you're designing with a dry coil, you don't need filters on the unit per ASHRAE. So if you have condensing coils, they require you to put MERV 6 and MERV 8 in the unit, which is obviously very negative, would negatively impact your induction rate through the chilled beam. So something to consider and keep the coil design dry for those reasons. Any questions on those items? So moving along to a study that Johns Hopkins did, they analyzed, from an all-air system and looking at a chilled beam type system, what are some of the benefits that they might realize when looking at these decoupled cooling systems? So really, on the next couple slides, what we're pointing out is the difference in ductwork, both diameter and size of the ductwork, but also the return air back to the rooftop unit is non-existent. So we just have your supply and exhaust ductwork that we have, and that really came into play when they were able to utilize. This was a render kind of simulating the amount of ductwork that they need to run for this particular area of a patient room. Patient rooms they had on a certain level. So notice that when we switch over to the other side, when you go to the chilled beam or decoupled cooling system, again, we're reducing the size of ductwork, which we've talked about a number of times just today, but that actually allowed them to, in their review, add another patient room to each level. So that had substantial impacts to not only the revenue for the healthcare system for Johns Hopkins, but also, it helped again with energy savings per year, and reduced actually their mechanical system savings as well. Okay, and then the last sort of case study that we're talking about here is University of Oregon. So this one is showing which type of unit do we think? Showing over above the printers. I think I just heard it. Passive beam, yep. So we've got kind of the spiral duct for the general air distribution, and then the passive beam is located, I believe, intentionally above the printers, so where you've got a lot of load in the space. So those are handling a lot of that space sensible load from the printers. Okay, so getting into design considerations, this is where we're going to get into some of those technical discussions. Won't talk about this much, but really there are unique principles or design aspects that we need to talk about when you're decoupling these two systems, because now, if you're not using a large amount of air to bring all of your latent and sensible conditioning in a space, you've got a reduced amount of air in that latent potential, we have to look at that and make sure that we're depressing the moisture enough from the outside air that's coming into the space to, appropriately account for, the latent gain within the space. So that's a lot of what we're going to talk about. Now, kind of zeroing into the chilled beams in particular, if we look at this high load lab space example, where let's just say there's 70 BTUs per hour per square foot, looking at a very top level view of the potential cooling capacity with these systems, this is again really what drives those energy savings, and kind of to try and get us thinking about in BTUs per CFM, or transfer efficiencies of the two types of system. All air, obviously, you're dealing with rho delta T CP, so that's typically 20 BTUs per CFM of cooling capacity. With a chill beam system, that's typically in the range of 60 to 80 BTUs per hour per CFM. So that obviously results in, and we've got a high CFM per square foot than office spaces or other spaces, because this is a high load lab space. But you can see a pretty substantial reduction in CFM per square foot, again, from that reduction of primary air. All right, so when looking at product selection, essentially showing all the different options that exist out there. Again, we talked about the Coanda wings as an option for open ceiling applications. Not as common, but you can integrate a return or even a supply diffuser within the space. I know it's a little difficult to see that, but if maybe for a lab space where you wanted to have additional makeup air in the space, you can add a foot or two onto the chilled beam portion itself and provide makeup air through that approach. Integrate the water valve enclosure in the space so you can drop down the face through the hinge and access those water valves. So lots of neat options to consider. Also the pattern controllers. So those can be provided to essentially shorten your throw. So yeah. Question.
Circulation.
Right. So that's been tested to essentially minimize or look at how much recirculation is. So with the discharge kind of moving away from that return, we try and minimize how much of that supplier is being pulled into that return. Let's see. And then when you're selecting primary airflow, a bit of an iterative process, but just taking into account the nozzle size and the amount of primary air that you're supplying to the space. All those kind of balance out in the end to provide your capacity. So it's very important. Not all beams are really equal in the sense they might look the same, but you could have different nozzle sizes and ultimately different induction rates, even if it looks like the same beam. And really that's just driven by the quantity of nozzles and the size or diameter of the nozzle itself. Okay, so when looking at humidity control, we obviously want to avoid condensation in the space. And, room conditions, this is pretty standard, so 75, 50%. That's at a certain moisture content or humidity ratio. But when you're looking at selection one, this was probably very typical for an all-air mixing system where you've got 55, 54. And because you have that large volume of air, you can handle a large amount of latent capacity with that air system at 55 dry bulb, 54 wet bulb. But when you're using a chill beam or a decoupled cooling system, such as a chill beam, you want to be able to depress that moisture down a little bit more to handle the latent load in the space and really dry out the air enough so that that reduced amount of airflow, say if it's reduced by a third, you're going to want 3 times the latent capacity per CFM to be able to handle that. So does that make sense? We've got less air that we're moving throughout the building, so we want to essentially dry that out a little more so that once you mix it and deliver it to the space, you're going to still achieve the 55-degree dew point in the space. So this is a common selection, and when we look at this afternoon, the selection software run through, probably going to see the default values being around 55 and 51.6 wet bulb is a pretty standard condition from the DOAS or rooftop unit. In terms of the static pressure design, I had already mentioned this earlier, but the max. So okay, I think we got a question that came in. Yeah, so usually you'll selection 2. You might even see a lower wet bulb in dew point. It just comes down to the balance of what you need for latent conditioning in the space, whether it's an office or classroom, and how much primary air you have, and that amount of depression, that drier air on the supply. So kind of comes down to the application, which we'll review later today in the selection software. Hopefully that answers the question. So the max static pressure is typically 0.8 inches of water gauge, and again, a lot of that is driven by you're getting close to the higher NC levels to where for typical NC 35 or 40. So that's usually the max, and typically what we would follow for the chill beams. And then the minimum, and this is kind of industry standard general guidance of keeping it to 0.2 inches or above. So if you want to design for a bit of turn down on the CFM, say if you're doing demand control ventilation and measuring the CO2 in the space, you could design those conference rooms or office spaces for peak load at 0.8 inches of water column. But if you wanted to ramp that down to 0.2 inches of water column to reduce the outside air to the space, you can do that. And really that 0.2 minimum is the reason for that is maintaining induction through the coil and keeping that velocity appropriately high for that negative pressure above the coil. Supply air temperature, both Matt and I have kind of mentioned this, can be anywhere from 55 up to 65 degrees because, again, we're inducing some of that room air up through that coil, and it might end up being higher than 55 degrees. For heating, 60 to 90 degrees in heating, and usually we try and limit, about 15 degrees delta from the set point, just to minimize stratification, just like any other, mixing type system. Otherwise, you get an air quality adjustment for that zone air distribution effectiveness difference. So the CFM difference from that would be roughly 50%, I think, in most nozzle sizes, going from 0.8 inches of water to 0.2 inches of water. So in terms of, if you look at the bottom right, we've got a control graph on there. Usually you want to try and limit the amount of airflow that you're providing to the space. So, on a slight movement from the set point in the space out of deadband, you would still have that airflow at the minimum possible setting to maintain the latent requirements in the space and just modulate that chilled water valve or the hot water valve. You can see these are mirrored. So the approach is the same. And then if you continue to move, the space moves past, beyond the deadband, continues to heat up, you would open up the airflow to condition the space. So key takeaways, again, primary airflow that's required, it's a balancing act. So just consider nozzle sizing. And again, we'll look at that in the afternoon session. Primary airflow for offices and classrooms usually dictated by zone latent. So it could be, 0.4 CFM per square foot of primary air compared to 0.2 or 0.3 for classrooms. And then obviously healthcare labs, those are dictated typically by the minimum air change requirements. All right, on the water side, we've got, the key consideration here is maintaining that supply chilled water to above the dew point in the space. And typical guidance is 2 to 3 degrees Fahrenheit above the dew point in the space. And that'll keep you from condensing quite effectively. And in fact, you have air movement across that coil, so it's not a just a chilled radiant panel surface where it's stagnant air. Instead, you've got the chill beam is inducing room air across that coil, which kind of helps alleviate, condensation developing. Typical rises in temperatures for chilled water are 5 to 6 degrees. And then, 10 to 20 degrees on the heating side. Water flow rates 0.5 to 3 GPMs is typical. 0.5 just trying to keep away from it being laminar and having erratic performance or behavior. So those are common. And then again, we've already talked about this on the earlier session, but you can do 2-pipe versus 4-pipe to achieve heating. Okay. And then sorry, it's a little angry on that first bullet point. No anger intended, but just that condensation is not instantaneous. We've had very few, and Matt, I don't know if you could speak up to anything that's come up on your projects here locally that we've done, but really the only condensation issues we've had with the dry design is really startup. So if they don't dry out the building, or if they're not running the air handling unit and they turn on the chilled water, that's an issue. Or if the air handler went down, I think that happened in Florida, but they didn't cut off the chilled water. Obviously, the air handler going down is a significant issue. Just educating the facility is really key to make sure they understand that. I'm yeah. So for those online, Matt agrees. Matt, stamp of approval. So the ways to monitor and have a control loop developed for humidity control, we really want to measure the humidity within the space. Condensate sensors on the chilled water supply are great, but really as a reactive approach and maybe a second stage of condensation, but you really want to have humidistats within the space. So you're measuring the humidity and you can see that kind of, get more humid in the space and adjust the chilled water to the space accordingly. So really just doing that through chilled water reset and measuring zone humidity in the space. And then kind of closing out the water side. And again, I know I'm getting really close to lunch. I promise I won't run past getting us some food. But the traditional chilled beam system, again, we're dealing with 58 degrees Fahrenheit of supply water to the chilled beams. So want to talk about the different control or water loop strategies and how you might achieve that on projects, both large and small, because you might not have 58 degrees that's running throughout the entire building. So first one up is dedicated chillers. So, oh, is that a question? So for heating, passive would not be, oh, for redundancy, not passive beams. Yeah, I think on you might see some redundancy. I don't know if they're referring to like the boiler side. We wouldn't see passive beams for heating, but on the chiller side, I don't know if Matt, maybe you could chime in. So redundancy on the hot water side, I think is what they're asking about on the system design. Oh, to maintain the building from freezing.
Setback. You wouldn't turn the system completely off. It might be off for a time being while the building is within the set point or the setback set point. But if it goes below it, the system won't come back on to be.
Yeah, so and I wonder if to that point he's talking about fin tube or some auxiliary system within the building to heat or warm up. Yeah, I mean we've seen some projects with fin tube, low level at the perimeter and active passive beams. But I think that's driven by maybe just the comfort locally of their design. You know, because we've done a number of projects in the Boston area with Buckley that, you know, we're handling all the heating at the perimeter with just the chilled beam. Um, but yeah, to Matt's point, for those that were online, you know, really, you know, on off hours, besides having, you know, glycol in the water as well, if you've got four pipe, you know, to help in terms of the media, not to keep from freezing, but also, you know, still running a part of the system throughout the unoccupied hours to maintain, you know, temperatures and not have anything freeze. I hope that helps to the person that asked the question, but we can chat afterwards or reach out to us to discuss further. So as far as dedicated chillers, um, you know, it helps with independent control. Um, sorry, I thought I had an animation there. Independent control. So you've got two chillers here, the low temp, which is providing the 42-degree water to the DOAS air handling unit, in the fan coils in the entrance area. So, you know, where you've got possibly a lot of intermittent and frequent moisture gain from the outside. In entryways, lobbies, you could have fan coils still run off of that low temp chiller, and then have a separate medium temperature chiller, which is providing, you know, 58 degrees or warmer to the chill beams. Correct. Yep. So that is economical and a good approach for, you know, high-rise, large headquarter campus buildings, where they can utilize those independent chillers. You can also have a closed loop mixing valve, which we'll show in the following slides. Similar to the mixing valve, you can also use a heat exchanger. So you remove the valve and put a heat plate frame heat exchanger in there as well, and that essentially just moves the energy from, you know, return loops into that supply to the chill beam loops, but then also the district loop. So if you have a district chiller plant, there's ways to design those to accommodate the higher chilled water. And then I know on some projects, been able to utilize the warm return water off of the DOAS unit or air handling unit to run that into the chilled beams as well to, you know, improve efficiencies. So here's an example of where you've got a low temp chiller, and you can see that now it's not 10 degrees delta, it's 12 degrees because we're able to further lift that rise in water by providing the return 62 off of the chill beams back into that low temp chiller return loop. But essentially that mixing valve is the addition here on this graphic with the secondary pump for the chilled water loop for the chill beams. And then quite similarly, maybe more security with this type of heat exchanger, but you've got the plate and frame heat exchanger that's introduced into that where that mixing valve was to provide that energy transfer and the warming of the chilled water loop for the chilled beam. So kind of along that same vein, you'd have a heat exchanger or mixing loop if you have a central plant. So you can, again, just bring in that 42-degree water, whatever is provided from the central plant, and mix that to get it up to our chilled beam water set point. So very similar, just slight nuances in the system, looking from a high level point of view. And then like I mentioned earlier, if you have a latent design, you know, maybe it's a retrofit existing building application where you are still dealing with 42-degree water or cooling water, you can just use the latent or the wet coil style chill beam where it's got drain pans in it. So this is what it looks like. This is a video taking in our lab with the face brought down, and essentially we pumped that lab room to get it as humid as we possibly could and ran you know, subcooled water to the chill beam. So you can see that because we're inducing room air through that coil, it's very low velocity. We don't have 500 feet per minute. even 300 feet per minute running across those coils. So it's really low velocity and it doesn't have any of that condensation detach from the coil. So that just drips down to the edges on either side here into that drain pan that you saw. Let me try and. Do you see this insulated drain pan that runs around those chilled water coils? So again, that's that A-frame style unit. So there you would need, condensation management, obviously, so that's something to consider. So there's numbers of ways to integrate different services. You could put the lights into the Coanda wings as well. So, factory could provide openings to allow for those lights to drop down into that space. Or you could have, factory mounted LED strips as well. So, if you think the office space, the healthcare application, where you've got lights and beams very closely coupled, this could possibly decongest, I think that's a word, decongest the ceiling system to provide a benefit there. We've also done a number of projects where kind of concealing the piping on the backside of the chill beam as well. For those clients that are, sorry, I'm not making noise on the mic there. So for clients that are interested already using bipolar ionization as a way to provide effective air changes to the space, this is an option as well that you can integrate the BPI module into the chill beam as well, provided from the factory. Adjustable nozzle. So this essentially has a Allen key tool that allows you to adjust the nozzle size on each of the beams itself. So if you wanted to maybe have that flexibility as the business evolves and you change spaces from conference rooms and break that down and make more office spaces, you can adjust that nozzle to account for any outside air requirements that might be changing in that space. So essentially those calibration charts would still exist, but kind of saying that you don't have to, you're not set and stuck with a certain nozzle size with this approach. Okay, last part of the design considerations. I'll go through this rather quickly because we've got the printouts and PDFs with the data afterwards. But essentially, we wanted to point out that because chilled beams need that static pressure in the plenum, and it could be, again, 0.2 up to 0.8 inches of water column, the duct pressure between the VAV, if it has a VAV terminal box, and the beam has to be higher pressure than what a typical overhead VAV distribution system is. So, that can lead to significant impacts in pressure drop that we have to account for in our design. So straight duct with flex, you can see here, again, I know this is hard if you've got the paper in front of you, that might be a little easier to read. But you can see that the pressure drop going from 3 diameter straight duct to some amount of flex duct. So we've got 5 feet of straight flex duct. The pressure drop went up threefold just by switching to those different types of ductwork. And it's very common for chill beams to have flex duct connecting up to the inlet itself, because you might have round inlets or oval inlets. So that's pretty common. Now, surprisingly, maybe not surprisingly to those in the room or listening online, is that when you, and I know nobody's ever seen this on a job site, right? We don't have to put around a signature for this, but essentially if you have some crazy condition on the inlet from the ductwork, say if you're running ductwork and the elevation change, you have to kind of snake it down to the chill beam, creating an S-like curve, that's going to have a significant impact on the beam. And we really need that pressure within the beam to get the performance. So you can see here that the pressure drop just between those is 0.327 of added pressure drop just between those different conditions of the flex duct. So the top graph is showing maintaining the same duct pressure for the VAV upstream. And the bottom one is how much static pressure do we need in the ductwork if you wanted to maintain the same CFM to the beam. So hopefully that's kind of clear and makes sense. So you go from 0.53 inches to 1.33 inches of duct static pressure needed just between the difference in inlet conditions. And then this is just showing the differences. These are not typically conditions you would have running to a beam with 10-inch diameter ductwork, but showing a higher CFM, 1000 CFM running through 10-inch diameter ductwork, spiral duct to flex fully extended, and then 5% compressed. You can see that there's actually, obviously with the higher velocity air movement in the ductwork, that can have, a decent impact just if you have, spiral versus flexed, if it's completely straight or slightly compressed. So you're going from roughly zero static pressure difference to a quarter an inch. And then moving over to here, just introduces again that idea of those S-bends with the higher velocity in the ductwork. And then, it's very often that we see, especially in the sort of New England area designs, where we've got a VAV box that is controlling the airflow to the beams. So that'll be ramped up and down based on the needs in the space, whether it's CO2 or cooling or heating. And then at each of the beams, you'll have a trimming damper, kind of like what's shown here. So that essentially just allows us to, you're gonna have different static pressure requirements on a branch of ductwork, a common branch. So you're gonna be able to set those with that trimming device at each of those beams. But make sure we install them, 5 duct diameters upstream so it doesn't have any impact. There's also these auto-regulating dampers. You've probably seen these before. So those are balanced and designed with weights or springs to essentially adjust for the incoming air, the changes in static pressure to get the same CFM that you're trying to get. So maybe if you have a constant volume ductwork or no VAV upstream, you can have these that if that static pressure changes in the ductwork, you can still maintain the CFM to the chilled beam. So duct leakage with these types of systems, just I guess a general note to make sure that we classify the ductwork appropriately downstream of the VAV to the chilled beams. And Mark is going to talk about this in the afternoon session after lunch, which I do promise we'll get to very soon. But just want to show you a very brief example of if you've got a square plaque diffuser, all air system, again, traditional approach design, at 100 CFM, typically you're at 0.016 inches of water pressure drop. But with a chill beam at 100 CFM, again, because we need higher pressure to drive the nozzle velocity up, we're just shy of a quarter inch. So you've got significantly higher static pressure at the beam, which means that leakage is going to go up, in your ductwork. So just making sure that, ductwork has the proper sealing classifications. That way you have, we're able to get the CFM to the chill beams because, those small little holes and penetrations can have an impact. So for an example, the trimming device I had showed earlier, this was a particular version that you could see. It's got a square shaft going to the ductwork that was installed, but the opening is not square and it's round. So that's going to create what? That's an easy one. Leakage. Yep, leakage. So, and when you get up to 0.8 inches or higher of static pressure, it can impact through several CFM of the what we're driving from the VAV down to the chill beam. So just something to keep in mind, making sure we specify right auxiliary components. Okay, last part, just summarizing in these couple slides here that utilize us, reach out to us and Buckley. We're happy to provide our facilities. If you've got unique needs or maybe a client that hasn't used chill beams, but they want to kind of investigate it and see it in action, we could take them to projects nearby or utilize our hydronic test chamber, which is essentially a walk-in cooler with radiant panels everywhere in the space, and that's really dictated by ASHRAE 200 and other standards for radiant and chilled beam testing requirements. So all of our catalog test data is tested within this chamber that we have up in Winnipeg. There's good times and bad times to go up to Winnipeg, Mark. I mean, I don't know. Like it's all good, and it's an experience if you want to go in January. But maybe we consider the shoulder seasons. I actually like the adventure of walking to the hockey game in -40. I mean, I think everybody needs to experience that. Yeah, yeah, that's right. They say that's healthy for circulation. So those online, Mark agrees. We just confirmed. Specific mock-ups, we've also got other spaces that can look at, in situ certain project requirements that we can build and test. So you can see on this top right one, we're looking towards the wood slats, but this is a question that we get quite often is, if you have architectural wood slats in the ceiling, but the chilled beam is above it, we can, paint the chilled beams any color really, but what happens to the air distribution when you're behind wood slats? So just make sure the discharge direction is parallel to the wood slats. And, we've got a number of studies and things that we can provide you for assistance there to guide in those conversations. We've also, this was a project locally. This was not wood slats. This was a crazy waffle type ceiling or honeycomb looking ceiling, which would be a different impact than, wood slats that you can orient the discharge to. So, we're happy to look at all those unique decisions or the requirements and project details. And then fluid reality. So we've got in-house CFD as an option if you wanted to look at that, and we can even put that into fluid reality. This is not something that has gained significant traction, but sometimes it's helpful for architects or the owners to see the space in a virtual setting, before you build it, because it's a lot easier to make changes to a building before you build it. So this is a depiction of a classroom. We even went into putting the apples on the desk, just noticing that. Looks like I was going to try and say an apple type. I'm not going to go there. And then selection software. So we're going to show this again in the afternoon session after Mark goes through a couple of good topics on DOAS fan terminals and combining them with chill beams. Just during lunch or in the meantime, if you want to follow along with the software selection session, it's hard to say really quickly, go ahead and download that from the Price website under the resources and software. So that way you can kind of follow along. We can answer questions as we go through it. Just a quick note on that.